Okay, this unit covers probability. So like I said, a lot of numbers. We're calculating the likelihood of something happening. I told you the other day, I love probability. Students tend to have a love-hate relationship with probability. Some people like it because it's kind of fun, but also it can be very counterintuitive. And there's some tough things that we're going to get into.
One of the reasons I like math is because it's relatively intuitive.
Okay, well, that's going to change this time. It's not going to start out too bad, but once we get towards the end, the probability questions are going to be tougher. What we're going to talk about today, we already have talked about this a little bit last class, interpreting probability, so the likelihood of something in the long run. But the big thing is we are going to talk about simulations. So last class we used a simulation. That was the applet that you guys used when the teacher was shooting the basketball. We are going to design that, though, now from our end. So you could find this page of notes, please. This is where we're going to get started. As a special promotion for its 20-ounce bottles of soda, a soft drink company printed a message on the inside of each bottle cap. Some of the caps said, "Please try again," while others said, "You're a winner." The company advertised the promotion with the slogan, "1 in 6 wins a prize." The prize is a free 20-ounce bottle of soda. A stats class wonders if the company's claim holds true for the bottles at a nearby convenience store. To find out, all 30 students in the class go to the store, and each student buys one 20-ounce bottle of soda. 3 of them get caps that say, "You're a winner." Does this result provide convincing evidence that the company's 1 in 6 claim is inaccurate? Design and conduct a simulation to estimate the probability of getting 3 or fewer winners if the company is telling the truth. Okay. So the question is, do we have convincing evidence, convincing is key, that the claim is inaccurate? So what we should be asking ourselves is, what evidence do we have? So the claim is 1 in 6 are winners. What evidence do we have that that is inaccurate? Well, out of the 30 students in the class, only 3 of them were a winner. If we simplify that, of course, that's 0.1, which is less than that 1/6. Now, we have to ask ourselves, though, what are the 2 possible explanations? What's one of them?
Well, one of them is Ferdy was not a large enough did not have enough samples to figure it out.
Okay.
To get to it.
So we had a small sample. That relates to an idea in stats. What do we call the idea that different samples are going to give different results?
Sampling variability.
Sampling variability. So is it possible that the 1 in 6 claim is true and we just happened to get a sample that had less people winning? Okay. So first possible explanation is just sampling variability. So that would be the company's claim is true. We, or the class really, we just happened to get a sample where only 1/10 were winners. So it could be that if we went through every single bottle in the whole store, that 6 of them, 1 in 6 would be winners, and we just happened to choose a sample where it was less than that. What is the other possible explanation?
The company's lying.
Company is lying. Yeah. Thank you. So what we mean by that is 1 in 6 winners is not true. So the question then is, which of these is more likely? That's what we're trying to use with probability. Is we're trying to figure out if this 1/6 claim were really true, how often would we get 0.1 or only 3 winners? So what we're going to do is we're going to design a simulation and then we're actually going to carry it out. So here is our simulation. We're going to use a random number generator. What we need to do is we need to simulate the company's claim. So we need to set our simulation up in some way such that 1 out of 6 is a winner. So we are going to use the numbers 1 through 6. So we'll ignore everything else. We will let 1 be a winner. So then 2 through 6 are losses. So out of my 6 digits, 1 is a winner, 5 are losses. We are going to use a random number generator. With bounds 1 to 6. And we are going to generate 30 numbers. So we need to generate what the class actually did. The class bought 30 bottles of soda. So that's what we need to generate. These numbers do not represent specific people or specific items. They just represent, in general, win-loss. So we can have repeats. So we can't allow repeats. So we're going to generate these 30 numbers. We're going to have a string of numbers. What do we care about from those numbers?
How many ones are there?
Okay, so we will count the number of ones, which are the winners. Okay, that's what we're actually going to do right now. So I'm going to ask you to get out your calculator, please. Do you remember in your calculator where to find the random number generator?
Rand int.
And where would rand int be?
Math.
Okay, so you're going to go to math.
Go over all the way.
You're going to go to probability and rand int. And what I want you to do is you are going to do a lower bound of 1, an upper bound of 6, and you are going to generate 30 numbers.
How do you calculate?
Can I see your calculator? So that, do another comma, put a 30 in. So if yours needs commas, you're going to do 1, 6, 30, and that tells the calculator to generate 30 numbers. Or you can just keep hitting enter until you get 30 of them. Take 2 minutes right now, do that. Generate 30 numbers and count the number of ones, please. Okay, so then practically, here's what you do. You would never do a simulation once. So as we saw in the activity we did the other day, we did the simulation multiple times, right? She shot 100 times. So we're not going to have this class of 30 only one time. We would have all of you do it and count the number of winners to see the behavior. So what I'm going to do now is I'm going to make a dot plot, and you should do the same thing. And we are going to record the number of winners. So I'm just going to ask you to raise your hand. Did anyone get no winners at all out of their class? Ola? Okay. Anyone with only 1 winner? Okay. 2 winners? 3 winners? Okay. 4? 5? Okay, thank you. 6? Okay, thank you. 7? Great. 8? 9? Okay. Anybody with 10? Anybody with more than that? Okay, great. Perfect world, how many winners should we have gotten?
case to
Perfect world, how many should we have gotten? 5, right? 1 in 6 out of the 30, we expected to get 5. So this is what we expected to happen. And you're gonna notice we got a lot of 5s. I think it's pretty unusual that we got all of these above the 5s, but that just happens. Now, ideally we would have done this more times, but that's it. So if we wanna estimate the likelihood of this 1 in 10, so that's what we're trying to do. How likely is this 1 in 10 if 1/6 were really true? What you're looking for on your graph is where that 1 out of 10 happened and anything more unusual than that, which would be here. So what we're getting from this is the likelihood of 1 in 10. Well, I guess really 3 in 30. I'm going to do it unsimplified. 3 in 30. If the 1/6 is really true, we're estimating to be 3 out of however many there are on here. So 7, 10, 15, 19, 21, 24. So it happened 3 out of our 24 trials, which is about 0.125. So we've talked about unusual in stats is 5%. So what this is saying is if 1/6 were winners, 12% of the time, you would get a sample where only 3 out of the 30 were winners. So what that tells us is we do not have reason to believe the company is lying. So is there convincing evidence that the claim is inaccurate? No. No. We do not have evidence that the claim is inaccurate. And that is because our probability is bigger than 5%. It is not unlikely to get the result that we got if the company's claim were really true. The main thing today is this part in black, designing the simulation. You are occasionally going to actually have to carry it out and answer a question, but bigger is actually designing. I want to finish. I need like 10 more minutes and then we'll take a break. That work? Okay. A lot of this we did the other day, so we're going to go through it quickly. Law of large numbers says as the number of repetitions increases, so number of repetitions or the number of trials increases, our proportion, also our relative frequency, that's the other term that you're going to see, our proportion or our relative frequency is going to get closer to the true probability. So our probability up here of 0.125, probably not that accurate because we only did 24 trials. But what we could do is set up a computer to carry this out 1,000 times, and we would be more likely to get the correct answer. A probability is the percent of successes in the long run. In an interpretation, you have to say long run. You have to either say long run or many trials. So large number of trials. Okay, 2 things for you to know. First of all, probability is always between 0 and 1. So please do not tell me that the probability is 40%. That doesn't make sense. And then the other thing that I need you to be aware of is be aware on your calculator of scientific notation. So I'll have students tell me the probability is 2.4. It's not. It's probably in scientific notation. It's probably a small number. Okay, so if I were to ask you to interpret, the probability of getting a sum of 7 when rolling 2 dice is 1/6. If we were to interpret this value, we would say, in the long run, if I rolled 2 dice many, many times, about 1 out of 6, or if I wanted to put that as a decimal, about 0.167 of the time, I would roll a sum of 7. I got one more thing to write down, and then we'll take a break. Questions? Okay, some myths about randomness. There's 2 that I need you to know. The biggest mistake is applying the law of large numbers to a small number of trials. So that would be, for example, the first example that we did, if we said the probability is really 0.125. It's not. 24 is not enough trials. And then the other big mistake is using the past to predict the future. Like flipping a coin. So if I flip a coin and I get 4 heads, and I ask what's the likelihood I get a head on the next one, still 1/2. It doesn't matter, assuming that it's a fair coin. But just because you flipped 4 heads doesn't mean that you're going to get a head again. So now we're going to get into the actual notes on simulation. So firstly, what is the purpose of a simulation? To estimate probabilities that are difficult to calculate theoretically. So for when we get into calculating probabilities, for the most part, we're going to be working in a theoretical world, perfect world, but sometimes it's difficult to estimate those probabilities. So here's what you need when you are designing a simulation, just like the simulation that we did before, for the first example, that is. 4 steps. The first one is describe what the numbers represent. And then you need to tell me, is it with or without replacement? What I mean by that is, what do I do with repeats? So in the last example, we kept the repeats. Third step is how to carry out the process. Which includes the stopping criteria. So in the last example, we stopped at 30 numbers. And then the last thing is you are going to tell me what to count.
What's that word say after carry out?
Process.
Oh.
Plus. Okay, you have a whole bunch of different options for how to do a simulation. The most common one is what we did, a random number generator. And then I'm just going to say other. Here's what I mean by that. Maybe you decide to use dice. That's pretty limited, only has the numbers 1 to 6. Maybe you decide to use a coin. You know my favorite is the good old hat. Or you might use a table of random numbers. A lot of times, you will be given the option to choose one. Sometimes I will force you to use a random number generator or the table. We are going to do one more example together. You all will do one example, and then that will be it for these notes. Do you guys remember the first day when we watched the video about Joy and she was smelling the shirts and she could identify Parkinson's? Okay, we're going to design a simulation around that. So as reported by the Washington Post, Joy of Perth, UK, smelled a subtle musky odor on her husband that she had never smelled before. When he was diagnosed with Parkinson's 6 years later, Joy suspected the odor might be the result of the disease. Scientists were intrigued by Joy's claim and designed an experiment to test her ability to smell Parkinson's. She was presented with 12 different shirts, each worn by a different person, some of whom had Parkinson's and whom did not. The shirts were given to Joy in a random order, and she had to decide whether each shirt was worn by a Parkinson's patient or not. Assuming she is guessing at random, what is the probability that she will guess correctly? Come on, guys. How many options are there? She's correct or she's incorrect?
50%?
Yeah.
45, whatever.
One thing I want to point out before we do B, why does it matter that these are in a random order? That's very important. It relates to the test you just took.
Because if they're not in random order, it's just like, it leaves it like,
Why it matters that the shirts were given in a random order? One might say they were randomized. Millie?
It like indicates causation, not association.
Because it makes this an experiment. Okay, that's what matters here, is that random order makes this an experiment. Why do we care? Like Millie said, we could show cause and effect. Okay, so now let's get to the actual simulation part. In the original experiment, she correctly identified 11 of the 12 shirts. Does this provide convincing evidence that she can in fact smell Parkinson's? Design and conduct a simulation to estimate the probability that she would correctly identify 11 or more of the shirts if she is just guessing. Okay. So here is where we're going to use this table. That's why I gave us a table of random integers. We need to figure out what our digits represent. So in the experiment, Joy is given a shirt, and she smells the shirt, and we want to know, did she correctly identify it? So our digits have to represent correctly identifying or incorrectly identifying the shirt. So we're not using the 12 yet. We need 50% of the time she's correct, 50% of the time she's incorrect. You can use 1, 2, 3, 4 digits, so on and so forth. I'm going to use 1 digit. So we have a few different options. We could use 1 and 2. 1 is correct, 2 is incorrect. What's the downfall of that?
that's a lot.
There's so many numbers that aren't two.
Did we see we're going to have to skip a lot?
E.
Okay, so what I'm going to say is let 0 to 4 represent Joy is correct. 5 to 9 is incorrect. So that's step 1. We are going to start at line 1 on the table. And look at 1 digit at a time. What happens if we get a repeat? Count it. Yeah. These numbers just represent correct, incorrect in general, not specific people or items. So we are going to say use replacement. You could also say don't skip repeats. Either one. She's looking at 12 shirts. So we will stop after 12 digits. And then the last step that people tend to forget is what we need to count. So we care how many correct identifications did she have. So we will count the number of correct identifications, which is the numbers 0 to 4. Okay, if you are asked to carry out a simulation, like you're given this table, you need to do so in such a way that I can follow what you did. So marking on the table, if we look at 12 digits, this is one trial. And then you would go through, figure out how many of them are correct. So that would be the 1, the 3, the 1, the 3. So if we're counting then number of correct, my first trial, there were 3. So then if I look for 12 again, this is 8, so that'll be my second trial. Again, do something where I know what you did. So I'm doing the dots. So I have 1, 2, 3, 4, 5, 6, 7 correct. And then you would keep going. We're not going to do any more. We're just going to do 2. Yes.
If it tells you to conduct a simulation, like how many trials do you have to do?
So I will specifically tell you how many. Generally, it's like 2 to 5. I'm not going to have you do a lot because it's not a good use of your time. Okay, one last line I want you to put in your simulation. This is really, really important. You need to say, this is one trial. We already talked about law of large numbers. We want a lot of trials. So you need to say, repeat many times. Okay. Questions? Okay. We got 2 more things to write down. One note, and then you all are going to do an example. Okay. Common errors when using a table of random digits. The first one is forgetting to tell the user where to start on the table. So start at line 1, start at line 105, whatever the first line is. And then the second error, this only applies to a table, not to a random number generator, and we've talked about this before. We need the same number of digits. So if we had 100 items, we cannot do 1 to 100 like that, because we have a mixture of 1 digit, 2 digits, 3 digits. If that were the case, we would have to do 0, 0, 1 to 100, so that everything has 3 digits. Random number table, doesn't matter. Okay. Questions for me before you do one? Okay. You are going to do this next example. I'm going to warn you, it's a little bit different. I want you to do it with the person next to you, and it says a simulation or it says a table or a random number generator. I want you to do a random number generator. So what I want you to do is think about very carefully what this looks like in real life. And then your simulation needs to accurately reflect what you're doing in real life. I want you to design the whole thing and do one trial. Move your desks together and please get started. Starting with the digits. So what's happening in real life? I'm choosing a name out of a hat. I need to accurately represent that choosing a name out of a hat. This one is different because these are different seniors and juniors. Like they're actually people. So we need to make sure we can accurately represent that we're not going to choose the same person twice. So I would use the numbers 1 to 90. You could say, for example, 1 to 60 is seniors. 61 to 90 is juniors. Did we get something like that? So then we're going to use a random number generator with bounds 1 to 90. Did we say that again? You have to specifically say bounds 1 to 90. Here's where I thought we might have messed up. Well, first of all, are we using replacement? No, because we don't want to choose the same person twice. When do we stop? How are we generating numbers? Can we just say generate 6 numbers or generate 8 numbers? Real life, what's happening?
Generate one number at a time.
Okay, yeah, we're pulling out names one at a time. So you should say generate 1 number at a time until you get 4 seniors and 2 juniors. And then what are we counting? The number of names picked. And then did we actually try to do 1 trial, maybe?
How would we like show you our work for the trial?
You wouldn't.
Okay.
If I'm ever going to ask you to actually carry it out, I'm going to force you to use a table. How do we feel about simulations? Feel middle of the road? Any questions for me?